All right, so now that we have identified the principles of induction and we've talked about how it's changes in magnetic flux, so changes in either the area of a loop that's exposed to a magnetic field or changes in the magnitude of the magnetic field that can induce currents, it's time to talk about what makes chapter 21 hard, which is figuring out the direction of the induced current. So I want to do a little thought process using what's called Lenz's law. So Lenz's law is going to be the set of procedures that will probably go on a note card for you all at some point. That's going to tell us how we figure out the direction of an induced current. So here we go. Now I need to be really careful, and I encourage you to be very careful when you're taking notes on this, to be careful to talk about the induced magnetic fields and currents as being separate and probably in a different color than the external magnetic fields and currents. Okay, so Lenz's law is a law that says that the induced field will oppose the change in flux. Remember, this capital phi is flux, so it will oppose the change in flux. Okay, so how we're going to do this is in 4 steps. So the first step is figuring out the direction of the external field. Okay, so B, E, X, T. And I'm going to draw all of the external things as being green. Okay, so here's what I mean by an external thing. And I did this as a demo in the last video. When I move a magnet down into this loop, there will be a current that's induced in this wire. And we could measure that current just by looking at what was going on with the current meter. Okay, so as this, we know that magnetic fields always point out of north poles and into south poles. So actually the first step has been done for us here, which is that this line that points down, this is BEXT. All of these point out of the north poles and into the south poles. And actually this magnetic flux field doesn't just go straight down, right? Each one of these will make a loop and go up and around and back in like that, but we're going to ignore that for now. Okay, so I have that magnetic field, the external magnetic field. So this is external because it's the thing, this magnet is going to be inducing a current in the wire. So everything associated with the magnet is what we call the external stuff, and everything associated with the wire will be the induced stuff. Okay, so we'll say it points down. And is it getting stronger or weaker? So if we take a magnet and we move the magnet down, then I can say that as the magnet gets closer to this, the external field is getting stronger. Okay, so there we go with that. That's our first step. So now we're ready for the Lenz's law step, which is, so a current is going to be induced in this wire to oppose that change. So the fact that it's changing, it's increasing in its magnitude. Okay, so I induced will oppose the change. So let's think about this. As this external field gets stronger, the field that is we're going to induce a current in this wire, and this wire is going to make its own magnetic field. There's going to be, and it's going to oppose how much this is changing. So because this is getting stronger, there's going to be an induced magnetic field that looks like this. okay? So it wants to oppose the change, okay? The external field points down and it's getting stronger. Nature doesn't like it when things change. So it wants to have things go back to normal. So the way that it can oppose that change is by creating a magnetic field that is induced that points up, okay? So we don't yet know what the current is going to be in this wire, but we do know that however this current is, the magnetic field that's going to be generated by that induced current will be up in the middle of the wire. So I induce will oppose the change, and that's Lenz's law, which means that B induced points up in the middle of the loop. Okay, and now we're ready to use the right-hand rule. And we're going to use the first right-hand rule, the one that tells us how things go. So you put your thumb in the direction of the magnetic field, and you put your thumb in the direction of the current, and you want your fingers to wrap in the direction that makes it so that in the middle of the loop, the field points up. So I'm going to take my loop right here. I'll hold it at a little bit of an angle so it mirrors what's going on over here. And I want my fingers to point up in the middle of the loop. So that means that the way that I'm going to be wrapping this is like this, okay? So my fingers are pointing up in the middle of the loop, so that's my induced magnetic field points up. That was we got from the Lenz's law step. And that must mean that the current is going like this. All right, so what I'm going to do is I'm going to say that my induced current goes around like that. So if you were the perspective of the magnet looking down on this loop of current, the current would be going counterclockwise. Okay, so there we go. It says that I induced must be okay. So that's the 3 steps that you're going to do every single time that you do a Lenz's law problem. We figure out what the external magnetic field is doing and whether it's getting stronger or weaker. If the external magnetic field is getting stronger, then the induced magnetic field will be opposite to the external magnetic field. And that's what we had happen here. There's another option, which is that if the external magnetic field was getting weaker, then we would have a situation where the induced magnetic field would point in the same direction as the external magnetic field. And we'll do an example like that next. I wanted to do this one first. Okay, so we would say that current is coming out of the meter over here, and it goes around counterclockwise, and then it goes into the meter here. Current meters, I'm going to add a little bit of things just to get used to looking at current meters. Current meters always have a plus side and a minus side on them. When current goes in to the positive terminal, that will be something that was recorded as a positive current. So this would be meter is positive, which would mean the current is coming into this positive terminal. So this dial would not be at 0, but like that. Okay. So let's do the flip side. Okay, now let's take this same magnet, but now instead of having the magnet be going down, we'll have the magnet be going up. Okay, so we would say, let's move through our steps of Lenz's law. The first step is that the external, how is it pointing? The north pole of the magnet is still facing down, so these lines here are still going down, so BEXT is still down. Oops. And getting weaker. So what I mean by that is that as this magnet moves up, it's getting farther away from the loop. So from the perspective of the loop, the flux through this loop is going to get smaller, right? Flux is how many of these little magnetic field lines end up traveling through the loop. If the magnet is farther away, we have less influence from the magnet, and fewer of these lines will go through the loop. Okay, so BA external is going down and getting weaker. Okay, now we're ready for the Lenz's law step, which is that says that B induced will oppose the change. There's a little triangle to mean change. So because this is now going away, the change is to make this weaker. So because of that, B induced also points down. Okay, so a probably rule that should be written in Lenz's law here is that when BEXT gets stronger, B induced is the direction that's opposite to the external B. And then when BEXT gets weaker, B induced is in the same direction. So this is the example on this page. And this is the example on the previous page. And these PowerPoint slides, I printed them off to make it easier for me to work with, but the same PowerPoint slides are posted up on the wall. Okay, so B induced also points down, which means that if the external field points down, that must mean that in the center of the loop, B induced also points down. And this problem has actually already been done for us. So the induced current points down. And we could use the right-hand rule again, where now we want our fingers to point down in the middle of the loop. So my fingers point down in the middle of the loop, and that means that my thumb wraps in this direction. So the current is coming out of this positive terminal and into the negative terminal and around like this. So step 3 here, just to write it out, is by right-hand rule 1, I induced is out of the positive terminal and out of the positive terminal and into the negative terminal is a negative current. Okay, so that's the main problem-solving strategy that we're using for this. This is the hardest part of all of induction, is figuring out the direction of induced currents and induced magnetic fields. So there is a set of problem-solving steps. And we've been working through these already, but I'll put them here, right? The first thing is that we do is we determine the direction of the external magnetic field. And the second thing that we do is determine whether the magnetic flux is increasing, decreasing, or unchanged. Okay, so presumably in this step, I have been exclusively talking about how the magnetic field is getting weaker and the magnetic field is getting stronger. Another way that we could change the magnetic flux is make the loop bigger or smaller or rotate the loop in much of the same ways that we talked about last time. So we need to think about not just whether the magnetic field is changing, but whether the whole flux is changing. And then we'll say the magnetic field due to the induced current points in the opposite direction of the original field if the flux is increasing, or in the same direction if it is decreasing. And we missed this one before, but if the flux is not changing, then there is no induction, so it will be 0 if it's not changing. And then we use the right-hand rule to determine the direction of the current. All right, let's see if you got it. Try to do this question. Give it a pause and work through it. Follow those same steps, and then we'll come back and work on it together. Okay, So what I have here is a very similar setup. So now I'm gonna keep doing my green for the external fields. So I have the magnet is moving up, so it must be getting the external field must be getting stronger in the vicinity of the loop. And I also know that magnetic fields always point out of north poles. So I'll say that B external looks like this. So my first step is that BEXT is up and getting stronger. Okay, so because it's getting stronger, that means that B induced must point in the opposite direction. Is down. And remember, this came from these rules right here, right? The magnetic field due to the induced current points in the opposite direction if the original field, if the flux is increasing, okay? So that's where we are right now, right? The flux is increasing because the magnet is getting closer, so there's more magnetic flux going through this loop. So that must mean that the induced current in the middle of the loop points down. That's what the induced looks like. And now we'll use our right-hand rule to try to find a way to make the induced magnetic field point down in the middle of the loop. So that's how I do that. Now my fingers are pointing down in the middle of the loop. And when I wrap my fingers around it, I see the front of the loop is going to the left, and it's wrapping around this way. So here is what the I induced looks like. Okay, so when you are looking down on the wire, so here's the wire, and we have just determined that it's going around like this. On any test you take from me, whether it is digital or in person, you are allowed to bring a loop. So bring a loop and enjoy your loop. Practice using a loop. Get something that you can get used to. So the current is going around in this way. That way is clockwise. So this is a clockwise induced current. Okay, I have a couple demos I'm going to show you. Over here about this. So the first one is the thing that we have shown before, but we're going to show it again, which is that I have this demonstration galvanometer, and it's connected up to a loop of wire that you cannot see. So let's get this a little bit better. So it's connected up to this loop of wire right here. And I have a magnet, and you see the little N. So here's the north pole of my magnet. And this will be the moment of truth to see if I hook this up right, because I'm not quite sure right now. As I move this down in toward the loop, there should be a positive, the dial should deflect to the right. And there you go. Do you see it? So the dial, which is right here, deflected a little bit to the right. Now as I pull it up, the dial should deflect to the left. And there it went. Right, left, right, left. I can make it kind of go like that as much as I want. Okay. The other thing that I wanted to show you is something that is similar to this example with the magnets, only uses something called an electromagnet. So the north pole of the magnet has a magnetic field lines that point out like that. Okay, so we can think about anything that has magnetic field lines that point out one end as being the north pole of a magnet. And that's what I want to do here. So if I have this loop, right, and if I have current going around in this direction, then the magnetic field lines are going out and toward the camera here. So this is actually something that we could think about as being a magnet, where the north pole is over here on this side, on the direction toward the camera, and the south pole of this magnet is on the direction toward the other side. So if I put a current through this loop, it behaves just like a magnet. It's what we call an electromagnet. And that's what I have here. So right here, I have a solenoid. I'm not using this yet. I'm just talking about this right here. And this is just a loop of wire. And I'm going to put an extremely high current through this electromagnet. And I have this little piece of metal here to help sort of enhance the effect and also direct things. But it's just a loop of wire that looks like this. Okay, and so mine has 220 loops around and 2 things that go out to the other sides of this. And I'm just going to connect this. I'll show you what I have here. This is just 2 ends of an outlet. So I took an outlet off of something and I stripped off the edges. And now I'm going to just plug this outlet straight into the wall. So it'll be the 110 volts or so of current. And I have a switch to turn it on and off. So, it's quite a bit of current going through here because this is very close to a short circuit. So I have written on here that this is 0.6 ohms. So it's just like a wire with a very small resistance. So we have a really low resistance path between the positive and the negative terminals here, and it's going to have a huge current going through this wire. It's going to make a very strong electromagnet, okay? And as we do this, let me get this plugged in. I have a couple of little pieces of copper that I've made just in the shape of a square so that they can go around this right here. And so they're obviously not, connected to the solenoid, but they're going to be able to, when they are in the presence of this magnetic field created by this electromagnet, there should be an induced current in the wires, and that induced current is going to make a reaction. So let's see what it is. So I'll give it a little chance to do this. Call this the jumping wire demo, and I hope you can see why. By the way, you ever had an MRI done? You ever, and you get in the MRI and you hear all those like loud noises? Do they sound a lot like this? Right, the sound of the current, and actually what's the main noise here is that 60 hertz hum, because this is also oscillating at 60 hertz a second, or 60 cycles a second, is it's vibrating and making a noise. But that really high current actually makes noises that are audible, and that's why you hear those weird noises when you're in an MRI. So just to show you that this is something having to do with induction and not something else, I have the same thing here, only now this loop of wire is broken. So it's not a complete circuit. So I do the same thing with this wire, and I put it over my thing. I turn it on. Same noise, same current going through the solenoid, but there's nothing being induced in this little loop of wire here. So there's no interaction between the two of them. Okay, so and one thing that is just to talk about this jumping ring just a smidge more. I have this. Here's our jumping ring demo. So what has gone on is something akin to this. Okay, so I had the north pole of a magnet making an external field that pointed up, and as this external field points up, it's going to induce a current like this. So we have these 2 opposing fields here. So what is going on actually is pretty cool, which is that if you think about this, right, this is like the north pole of the electromagnet. And this right here, well, everywhere that a magnetic field points out of is the north pole of an electromagnet. So this is like the north pole of another magnet. The south pole of this electromagnet would be down here. We know that two north poles next to each other exert a force on each other. So the reason that that ring jumped is because we had two north poles of magnets right next to each other. They experienced an opposing force and made the rings bounce. Okay. Ooh, I perhaps should not have done that because now I don't know what my pieces of paper are. Okay. All right. So hopefully you feel a little bit more comfortable about figuring out the directions of induced currents. And now we're going to move on to figuring out the magnitudes of induced currents. And I feel like it's the theme of the semester that I have said many times, which is that figuring out the direction is the hard part. The magnitude is easy. So Faraday's law is going to be the formula that will tell us what direction the induced currents go. But this by far is a much easier thing to do. So here's Faraday's law. So it says that the induced EMF, so this here is the induced EMF or voltage. Okay, so you have is equal to the magnitude of the changing flux. So, and if you have many loops of current, then the induced EMF in those many loops is just this number multiplied by N, which is the number of loops. Okay, your book puts a negative in this equation. Okay, that negative is the reason they put that negative in there is because of Lenz's law. So Lenz's law says that the induced current and the induced EMF will oppose the change, okay? So it's a way of taking into account that whatever's going on with the induction is going to be opposite, okay? I don't like that negative. I think you use your brain to figure out the direction of the current and the direction of all of these things, and then you use the formula to figure out the magnitude. So I don't put the negative in there. I don't, because I use Lenz's law to figure out the sign. Okay, so Faraday's law gives the magnitude of the induced EMFs, and Lenz's law, which is the procedure we were just working on, gives you the direction. Okay, so with this induced EMF, once you have a voltage, you can figure out the current using Ohm's law. So Ohm's law is the one that says that the change in voltage will be I times R. So if you know the resistance in the loop and you know the induced EMF, you can figure out the current pretty easily. All right, so let's do an example. All right, so I have a 10 centimeter loop in two different magnetic fields, and we'll say that the loop's resistance is 0.1 ohms, and we want to determine the direction, so that will be using Lenz's law, and the magnitude, that will be using Faraday's law of the induced current. All right, so here is A, and again, I encourage you, pause it, do it yourself, and then I'll run through the answer. So if you've had a chance to look at this, let's go do A, and we'll do these 3 steps. So I have that my first step is that B external is out of the page, and I'm going to go ahead and just talk about the flux. The flux is increasing. Okay, so it's out of the page because of all these dots. The second says that because it is increasing, B induced is into the page. And of course, you know by now that what does into the page mean? Because if I have this loop here and I put my fingers like this, if current is going around in this direction, that means that the magnetic field is into the page on the inside of the loop, but it's also out of the page on the outside of the loop. So if in doubt, if you're ever not sure what we're talking about, think about the inside of the loop. The magnetic field is way stronger on the inside of a loop or a solenoid than it is on the outside of the loop or the solenoid. So that's what we tend to focus on. So I want the induced magnetic field to be into the page in the middle of the loop. And this just was a natural way for me to hold this, but it ends up being the right way. Right now I have my fingers are pointing in the middle of the loop, and that means that the current is going around in this clockwise direction. So our third step will be by right-hand rule 1, I induced is clockwise. Okay, so X is in here. So that's B EXT. And I called it EXT, but I meant to call it induced. And there's I induced. Like that. Okay, so that is the direction, okay? So I induced is clockwise. To find the magnitude of the induced current, we're going to use Faraday's law. So we'll say that the magnitude of the induced EMF is equal to the magnitude of the change in flux over the change in time. Okay, the formula for flux, be a great time to look it up and make sure that you know where it is on the equation sheet. But the formula for flux is B times A times cosine of theta. And so we get to ignore this cosine of theta. The way that I find is helpful to think about this is that the reason that this term, this flux, this cosine of theta term is in here is for the possibility that this loop isn't oriented like this, but that it's oriented at an angle. Okay, if as it changes its angle, the amount of flux going through the loop changes. So I have the most flux when it's right here, and I have less and less and less and less flux until there's zero flux right here. So the whole point of this is that when I have my loop like this, I know. Let's not worry about thinking about the angle. Let's just know that this equals 1 because this is oriented in the way that maximizes the flux to the loop. Okay, so cosine of theta is going to be 1 at most or 0 at smallest. I guess it could be -1 as well, but we're going to be taking the absolute value of it anyway, so that negative will go away. So all we are interested in is how the flux is changing. All right, so the flux is B times A. All right, so the B here is the external magnetic field. Okay, so this is B external times the area of the loop. The area is pretty easy, right? So that is, let me rewrite this a little easier way to see it. So this will be the final minus the initial. Right? A delta is always a final minus initial divided by the time elapsed. Absolute values in there. So flux final minus flux initial. We've been told this, that it's changing at 1/2 a Tesla per second. Okay, so let's say we start at time t0 and the magnetic field is 0 Tesla at t0. What is it at 1 second? It's 1/2 a Tesla. At 2 seconds, it's 1 Tesla. Right? Every additional second, it's changing by 1/2 a Tesla. So we can make up, right, if we're going from 2 seconds to 3 seconds, then this change in magnetic flux, or at least the change in magnetic field here, will be 1/2 a Tesla. If we're moving from 2 seconds to 4 seconds, then it will be 1 Tesla. So we sort of, it doesn't quite fit the equation in the way that is the way that we're used to thinking about it. But let's make up some numbers, okay? So let's say that t equals 0 seconds and B initial is 0 Tesla, okay? At t equals 1 second, B final is 1/2 a Tesla. Okay, and we can make up any numbers as long as they followed this relationship right here. So let's use those numbers in right here. Okay, so we'll say that the induced field is the final minus the initial, so that is 0.5 times the area. I suppose we should calculate the area. Let's calculate the area up here. Is pi r squared. So the area of a circle is pi r squared, so that'll be pi times the radius, which would be 5 centimeters, We did this exact in the last question. So this was is 0.0079 meters squared. So we'll do 0.5 times 0.0079 meters. I'm going to ignore the units so I don't run out of space. Minus the initial, which is 0, right? 0 times 0.0079, but I won't bother writing that. Divided by the time elapsed, and we set up our time elapsed to be 1 second. So the induced EMF is whatever these two numbers are multiplied times each other, which I wrote to be 3.9 times 10 to the negative third. Okay. Now we've figured out the magnitude of the induced EMF, and we figured out the direction of the induced current, and all that is left is to figure out the magnitude of the induced current, which is what we need as our final answer. So for that, we're going to use our old Handley Ohm's law, right? I know the voltage. If I knew the resistance, then I could figure out the current. If you go back and read the problem, I think you'll see that lo and behold, the resistance is right there. Okay, so we'll say that we know that V equals IR. So that must mean that I induced is the induced EMF divided by the resistance of the wire, which is 3.9 the negative third volts divided by 0.1 ohms. And that is 0.39 amps. Take a moment to look at the sig figs. How many sig figs do we want here? I see this number doesn't have a decimal, so I'll assume that that one is a 1 sig fig number. This one here is certainly a 1 sig fig number. So I'm going to round this to 1 sig fig and write it as 0.4 amps. All right. We're running out of space. I don't really have any space to do this problem, but I think we can still talk through it. So for this one, now the magnetic field is into the page. The external magnetic field points into the page, and it's getting weaker. Okay, so we'll start here. Piece of paper here, and say that our first step is that B external is into the page and getting okay. So before I write this, the external field is into the page, but what about the flux through this loop? Most of you, if you're tempted to say that the flux is getting weaker, then you would be wrong, because the flux in this configuration is 0. Right? There is no flux through this loop if the magnetic field is going straight into the page and the loop is oriented like this. That is that angle where no flux is through the loop. Okay, so it doesn't matter what the magnetic field does. There will be no current induced in this loop unless it has a little bit of a tilt to it. Okay, so flux is 0. Okay, so for this one right here, I induced is 0, and you're done. Okay, there's no induced current in this loop because there's no flux through that loop. Okay, next thing to talk about is a little bit of practical applications about how our houses work. So in our houses, we've talked about this a few times, but we never really explained why. We use AC voltages in our house. And the reason that we use AC and not DC is because, as we have learned, direct current, that's an unchanging current, doesn't work with induction. And our entire electricity grid relies on induction via things called transformers. And you've seen transformers before. They're these little gray cylinders that are on all sorts of telephone poles. You've also seen transformer stations. They're just like giant stations. There's one right on the Sage campus where power lines go in, and there's lots of transformers inside there. Okay, so let's talk about how a transformer works. Okay, I guess first a little reminder about the voltage and current vary sinusoidally in time. Okay, so what's going on with the wall outlet is that the current isn't just one thing. It's this number that's going up and down and up and down and up and down. And the reason that it goes up and down so much is that it is constantly changing. So there can constantly be induction going on in our electricity center. So this is what a transformer looks like, and this is how they work. So we have primary coil and secondary coil. Okay, so the primary coil, you can think of this in the Lenz's law way as being the external. Right, so the external field and the external field and the external all of that stuff, external flux, are going to be on the primary coil. And changes in this primary coil are going to induce changes in the secondary coil. And so when I've done this before, I have see if I can get enough stuff over here. When I've done this before, I've done this with just two sets of coils of wire, and they look like this. And I've put them next to each other so that they do some induction. Real life transformers are just this. So this is a real transformer. But as we've talked about, when you put, this isn't a magnet, it wouldn't stick to anything. I can touch it to my computer and it won't ruin anything. But sticking steel inside our solenoid makes our solenoids work better. So we get more induction that way. And so what goes on here is that when I set it up like this, right, there's going to be, if this is the external but primary coil, there's going to be a field here that's going to either go up or down. And if it's alternating current, it'll be going up and down and up and down and up and down. And this steel helps redirect the magnetic field so that it comes up and around and then down into the second one. This is how we usually build transformers, just because it's a more compact way. But you can also see that this pretty hefty thing. Have you ever plugged something into a wall? And now I'm wishing I had something easy with me, but I don't. When you plug things into the wall, they often come in these giant plugs. Like my laptop charger is huge. All sorts of things are huge. The reason that they are huge is because what those transformers are doing is they are usually step down transformers, and I'll talk about what I mean by that in a minute, that is taking the 120 volts that comes out of your wall outlet and changing that 120 volts into 6 volts or whatever it is that your electric thing runs on. And that stepping down, 110 volts is usually too much for stuff. So they change the voltage in a way that makes it safer, or whatever your device needs. So come back here and talk about this. So there's some formulas that talk about how the voltage and the current are related. So we have that the primary coil and the secondary coil, so the P's and the S's correspond to primary, and the S's correspond to the secondary. And of course, the secondary coil is where current is and voltage are induced in those coils. Okay, and so we can say that current, that this coil will step up the voltage. So this is a step-up transformer, and the reason that we call it a step-up transformer is because from the primary to the secondary, we have increased the number of loops, okay? And so in increasing the number of loops, we have stepped up the voltage. So if there was, I don't know, 10 volts here, there would be 1, 2, 3, 4 loops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if there's 3 times as many loops here as there was here. So if there's 10 volts going through this loop, then there would be 30 volts across this loop. Okay, so that's what a step-up transformer does, is it steps up the voltage. Inside all those things that you're plugging in your house usually is a step-down transformer. So we would have more loops on the primary coil and fewer loops on the secondary coil. So it would step down the voltage. And so there's some relationships here, right? As if the number of loops triples, then the voltage triples. And that's what I just kind of walked through here in words. And there's a formula that goes along with that. So N here is the number of loops. And of course, V is voltage. Okay. We can't get voltage for nothing, right? Energy still has to be conserved. So if we step up the voltage, we have stepped down the current. So that's what's going on here, is that this other formula has a, see how this one has a P over S? This one has an S over P, okay? So if the number of loops in the primary coil gets bigger, then the voltage in the primary coil gets bigger too, because these both are in the numerator. But if the number of loops in the primary coil gets bigger, then the number of loops in the secondary coil gets smaller. Excuse me. Goes that way. Okay, let's do an example. So pause this question and try to figure out the answer. So here's the answer. The answer here is A. So we said the primary coil keeps the same number of turns. So let's pull over my little demo of what a transformer looks like. But the number of turns on the secondary increases. The voltage will increase. Okay, so let's take this equation. So I have delta Vp over delta Vs equals Np over Ns. So we want to solve this equation for delta Vs. So when things are set up like this, I usually go with cross multiplying. So we'll cross multiply because we need to get this Vs in the numerator by itself. Okay, so we'll say cross multiplying means that we'll get to Np Vs equals Vp Ns. And now we'll solve for Vs, so we need to divide by Np on both sides. Now I'm going to make use of my eraser. Right. And we'll say that that happens. Okay, so if the number of turns in the secondary is increased, the number in the numerator gets the same, but everything else stays the same, then that must mean the left-hand side gets the same as well. All right, so the way that our electricity grid works is that it's all on transformers. So we like to, for energy conservation reasons, a high resistance has a very high, resistance, excuse me, I just lost my train of thought. A high current in a wire is gets really hot, and that wastes a lot of energy. So we don't look for high voltage. We don't want high current in our wires. So instead of having high current in our wire, we have high voltage in our wire. And let me explain what I mean by that. The ultimate goal of our transmission system is to transfer power. Okay, we want to get power from the power plant to our home. Okay, so you can have a lot of power either by having a lot of resistance. Why do I keep saying resistance? Either by having a lot of current or by having a lot of voltage. So high current is hot. Hot would be fine, except that heat is lost energy. So we don't want lost energy. We don't want something really, really hot. So instead of having high current, we have very high voltage. So transmitting power on power lines at distances is high voltage. Okay, so it comes out of the power plant and it's at a pretty low voltage. And then we go to a power station that looks something like this. And it steps it up to something huge, a really high voltage. So that we can have a pretty small current here, and so that like the amount of heat, the lost energy, will be pretty small. But we can't have 240,000 volts in our house because that is just too much of a potential. That's too much of a potential difference to be safe. So when we're ready to get to our homes, we send them to another transformer substation that step down the voltage. And then there's another, right at our house, there's another little step down transformer that transforms it all the way down to the 110 volts that we want in our house. And that's how our power stations work. And I am going to stop there and we'll pick this up next time.